Welcome back to ViViMaT. I know our next speaker personally. In fact, Antje Dollmann was the last science colleague I saw in person before COVID-19 made us all stay at home, and we sat on this very couch discussing her work. Antje has close ties to the Karlsruhe Institute of Technology, where she got her master's degree in 2018, before she started her PhD work there under the supervision of Christian Greiner. And today, she's even putting maternity on hold for 20 minutes to fill us in on the current state of affairs in her thesis. Please leave your questions in the box below, but before Antje begins, let's get some ideas where to publish next. Codings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, alloy.
Welcome to my talk about the deformation characteristics of cobalt, chromium, iron, manganese, nickel under tribological load. My name is Antje Dollmann and I studied material science at the Karlsruhe Institute of Technology. At the moment, I'm a PhD student in the group of Christian Greiner. I would also like to thank Stefan and Carsten for the opportunity to share my research here. I think most of you know that 23% of the world total energy consumption is caused by friction. This is why we try to understand tribological systems so we can decrease this number. Here you can also see the friction feedback loop. It says that the friction coefficient changes the surface stress, which can alter the grain size by, for example, subgrain formation, and this can change the friction coefficient. In my group, we have a special look on this part of the friction feedback loop, which is the microstructural evolution. And we have a special look on the really beginning of microstructural changes. And so one of our main questions is, how do metals and alloys deform under tribological load after a single trace experiment? So here you can see how all started. First of all, we investigated polycrystalline copper. This was electropolished to achieve a defect-free surface. As counterbody, a sapphire sphere with a diameter of 10 mm was used. Furthermore, we have a normal load of 2 Newton and a sliding velocity of 0.5 mm per second. Here you can see a stem image, and the tinfoil was cut parallel to the sliding direction in the middle of the wear track. Here on top you can see a protective platinum layer. This is necessary for the tinfoil preparation in the focused ion beam. Here on top you can see these two horizontal lines which were caused by the tribological loading. We call them dislocation trace lines. So in the next step, we added manganese to copper to investigate the influence of the concentration of solute atoms. An increase in the manganese content does not change the stacking fold energy. So you can see here that there was still a formation of the trace lines, so there is not a huge influence of the solute atoms. In the next step, we have here a brass system, and here the stacking fold energy decreases with increasing zinc content. So here with the lowest zinc content, you can still see a dislocation trace line. So here's also the higher stacking fold energy, and with the lower stacking fold energy, we can see a planar slip. And in my case, I'm investigating cobalt, chromium, iron, manganese, nickel. So this is an alloy with a really high content of solute atoms, and it has also a medium stacking fold energy, so we expected a behavior like here in this brass. And my question today is, how does this alloy deform under tribological load after a single trace experiment? Here you can see my first tribological system. So here is the cobalt chromium iron manganese nickel alloy. We have a silicium carbide sphere as counterbody in humid air. And we have again a normal load of 2 Newton and a sliding velocity of 0.5 millimeter per second. This system resulted in a friction coefficient of 0.2. You can also see here 2 stem images, and the temp foils were again cut parallel to the sliding direction in the middle of the wear track. Here in the first grain, we see again a horizontal line, and this could be a dislocation trace line. Here in the second one, we can see this band-like characteristic. I think it's easier to see here within the higher magnification. So I'm talking about these features. And these could be either twins or shear bands. To further investigate that, I have done TKD measurements. TKD means transmission Kikuchi diffraction, and it's the same technique as for EBSD. So both of the TKD measurements are shown here in sliding, normal, and transverse direction. Furthermore, I have plotted low angle grain boundaries in green, high angle grain boundaries in red, and twins in blue. So in the first grain, we see here this small angle grain boundary. So this is again a higher magnification of the surface near area. And we have also seen before that the dislocation trace line often has a low angle grain boundary character. And here in the second measurement, unfortunately, the resolution of the measurement is too bad, so we cannot say what these bands are. So here you can see the high resolution TEM image, which was done at the Institute for Nanotechnology at the KIT. So thanks my colleague Lakshmi Manta for that. So here is now the surface, and here is the line type characteristic. Here you can see the FFT analysis, and the red dashed line connects the diffraction points for the twin and the blue for the matrix. And now we can see here that this was clearly detected as a twin, and down here there's the twin not anymore. So I had a look into literature, which kind of mechanism can form such a twin. There's at one side the Venables mechanism, but for such a mechanism, the distance between the surface and the depth of the twin is too small for such a source to form. So by MD simulation, such a twin formation mechanism was shown. This means that chocolate partial dislocations start here at the surface and then glide into the material, and this is done on several neighboring 111 planes. And this is how the twin forms. So what we learn here is that these line type characteristics are twins, and for me it seems like that the twins form at the surface. I have used the TKD measurement also to investigate the misorientations. So here I have analyzed the misorientation profiles along the arrows in the TKD measurement. The distance of 0 microns means that there is the surface, and zero point 0.8 is in the bulk. And so we see that the misorientation has in both grains a strong increase starting at around 0.2 microns. And in the red profile, there's also a discontinuity, and this matches with the dislocation trace line. Furthermore, we have also a difference of around 25 degrees in the maximum misorientation of the two grains. And I think that this comes from the different initial grain orientations. We used the TKD measurement also to investigate the lattice rotation. Therefore, I have defined here these rectangles, and the orientations within these rectangles were plotted in inverse pole figures. Down here you can see the inverse pole figure in sliding direction. Furthermore, the initial grain orientation is marked, so here by a G, and also the surface orientation here and here. I usually compare these to what happens under uniaxial load because this is easier for me to imagine. And here in both cases we can see that here the orientation rotates along a bisector, which is quite well known from uniaxial tests because here are two slip system activated. And then something unexpected happened. So here close to this 113 direction, the orientation leaves the bisector. And one reason could be that the stacking fault behavior changes along this dashed line. In uniaxial tensile tests, the stacking fault width increases here in this part and decreases here in this part. And under compression, it's vice versa. And I actually think that this could be the reason why it's not furthermore rotating along this bisector. So we have seen that parallel to SC, the rotation is along a bisector with an expectation close to the 113 direction. And now we will have a look on the normal direction. Here we can see that it's rotating in the green grain from here to here, and in the red grain it's reflected at the bisectors. So here one time, here a second time, but this is quite normal based on the projection. I usually ask myself which direction is the responsible one for the twin formation, and therefore I have a simplified model which you can see here. I actually think that there is compression parallel to SD, then compression parallel to ND based on this normal load, and then here behind the sphere tension parallel to SD. And now we have a look on the inverse pole figures. We see here that the initial grain orientations are quite close to each other. So I actually think that SD was in this case not the important direction for the twin formation. And what is here quite interesting that we see that the green grain rotates from the part of the IPF where the twins are favored under tension is rotating here in this part where twinning is favored under compression. And here in the surface near area, we have seen the twins. And this is why I think that the lattice rotation leads to the twinning and that the compression parallel to ND is responsible for the twin formation. Okay, then let's also have a look in the transverse direction. There we see the lattice here, it's quite stable. So we have nearly a rotation around the transverse direction, which was also shown before in literature. Here I would like to show you the influence of an increasing friction coefficient. Therefore, I have changed the counterbody to a sapphire sphere and the atmosphere to nitrogen. The resulting friction coefficient was 0.5 in comparison to 0.2 of the other system. I think it's quite obvious that here the deformation layer is much thicker than in the system before. We see here also different microstructural characteristics. First of all, we have here really large twins, and the size of these twins is also one point why I think that they were formed by a Van-Abel's mechanism, and the other point is that some of these twins are not interacting with the grain boundary or the surface, and yeah, the Van-Abel's mechanism usually form in the grain interior. So then we see also a nearly straight grain boundary, and above that you can see the elongated subgrains, which were also published by Hugh and Hansen. Directly below the surface you can see some nanocrystalline grains. So here we have now also two zones, one which is dislocation mediated, and in the other zone we can see twin-induced plasticity. Summing this up, we have seen different microstructural characteristics, which is the dislocation trace line and the twins. And it seems like that the leading deformation mechanism depends on the crystal orientation. For the twinning mechanism, we have seen two different formation mechanisms. On the one side, the glide of stacking faults on neighboring 1-1-1 planes, and on the other side, the Van-Abel's mechanisms. And it seems like that lattice rotation can promote the twin formation. Concerning the dislocation trace line, we have seen that this can be also formed in a material with a medium stacking fault energy, and it has the small angle grain boundary characteristic parallel to the surface, as we have seen it before in copper and its alloys. So thank you for your attention.